Welcome back. In the last lecture, we were discussing about the behavior of the characters of a finite abelian group. So, in our setting G, a finite abelian group, G hat, this is the dual of G, which is the set of all characters on G, gamma of x plus y is equal to gamma x into gamma y, and then we had given the notation C G to be the set of all functions, complex valued functions on G. Then what we have shown that the number of elements in G hat is same as number of elements in G, and if number of elements of then let us say gamma I from 0 to n minus of 1, this are all the characters of G, and they form an orthonormal basis for C G. With this inner product, f comma G is equal to 1 over mod over G, summation over x belongs to G, f of x, G of x bar. Now, so if f is in C G, then we define Fourier coefficient or Fourier coefficient of f as f hat at gamma, this is equal to 1 by the cardinality of G, x varies over G, f of x, gamma of x bar, for gamma belongs to G hat. This is what it is called the Fourier coefficient, and the Fourier series of f is summation over gamma varies over G hat, f hat gamma, then gamma of x. That is what the Fourier series is. What is the inversion formula says? Now, we need, so inversion formula, from our previous experience, we would expect that f of x is equal to gamma over varies over G hat, f at gamma, gamma of x. This is for all x belongs to G and f in C of G. So, this is what we would like to prove. Now, first let us see f is in C G, and G hat forms an orthonormal basis for C G. Therefore, thus as G hat and ONB for C of G, therefore, f of x, this is equal to summation over gamma belongs to G hat, alpha of gamma and gamma of x, this is true for all x belongs to G for some alpha gamma belongs complex number scalar, because it is going to be the linear combination of all those gammas in G, it is a basis. Now, I take an eta belongs to G hat, then f of eta, this is equal to summation gamma belongs to G hat, alpha gamma, gamma dot and eta. So, this is it is a finite sum. So, we can pull out the sum, and then this is also we can pull out alpha gamma, then this is gamma inner product of eta. Now, we know that they satisfy the orthogonal properties, the characters. Therefore, this is going to survive only when gamma is equal to eta. So, this is so, and what is our f of eta? This is 1 over mod g summation over x varies over g f of x eta x bar. This is nothing but f hat at eta. So, thus f is equal to summation over alpha eta is equal to f hat at eta for every eta belongs to g hat. Therefore, this is gamma varies over g hat, this is f hat of gamma, gamma of x, that is what is called the Fourier inversion. So, we have got the Fourier inversion. Now, another important thing in the Fourier series course is to get the Parseval identity or the Plancherel theorem. So, this is dt or Plancherel formula. Okay. So, now as we recall for the Fourier series case, we got that this is 1 over 2 pi 0 to 2 pi mod of f of x square dx, this is equal to summation over n mod of f hat of n square, that is in the Fourier series. And so, this we call as the norm of f square, and for the case of Z n, what we have got similarly the norm of f square, this is equal to summation over n is equal to 0 to n minus 1 mod of f hat of n square. Rather, there we have denoted f hat as capital of N. Okay. So, here also we would like to get the similar thing that was all happening because of the orthogonal relationship of the characters in both the setting, and now we have the orthogonality relation. So, hence we can have, let us start with, which is by definition. So, now this is equal to summation over gamma varies over g hat by inversion formula f hat of gamma, gamma and summation over eta varies over g hat f hat of eta eta. So, now all these are finite sum. So, we pull this out, this is gamma belongs to g hat, eta belongs to g hat, and f hat gamma is independent of x. So, this is, and on the from the second coordinate, if we are taking f hat of gamma, this will appear with a bar conjugate of this. So, this is gamma eta. Now, if I do perform the eta integral first, eta sum first, then this sum, this quantity is going to survive only when gamma is equal to eta. So, this becomes gamma belongs to g hat. Now, f hat of gamma, now eta has to be, and then gamma gamma is 1. So, this is nothing but so that is what we have also we derive the Parseval identity or the Plancherel theorem for a finite abelian group. So, just to put it on record, we write that the theorem inversion and Plancherel holds for finite abelian group. Okay, so successfully we could derive the basic facts about the Fourier analysis in the setting of finite abelian group. So, it is a natural question that one would like to ask at this stage, that what are the other setting in which we can extend this theory of Fourier series. So, before addressing that issue, let us see some use of this Fourier analysis on finite abelian group in number theory. So, basically I will not give the entire proof in glory details of all the results what I am going to state. However, I mean I would try to sketch and give the outline as well as pointing out what are the difficulties, but just to give an appropriate direction in which you can proceed further on your own. Okay, so, now let us talk about little number theory with the elementary number theory. So, what we know is that one of the first thing we know that if n is n belongs to n, then it has prime factorization and also this is unique. That all of us we have learned at a very early stage. Just to a quick recall that if we do not have, suppose this is not true, then we must arrive at a contradiction, and that is that you take the set S which is equal to set of all n belongs to n such that n does not have have prime factorization, then what we are assuming, suppose S is non-empty, then what you can do is that it is a subset of the natural number. So, it will always have a least element. So, now let n naught be the least element of S. Now, certainly n naught cannot be a prime. If it is a prime, it has a prime factorization. So, it has to be a composite number. So, now n naught would be a into b, where both a and b they are greater than 1, a is greater than 1 and b is greater than 1. Now, both of them are less than n naught. Now, if they have prime factorization, then both a and b they have prime factorization, then n naught will have prime factorization. So, if a and b have prime factorization, then n naught also has prime factorization, but which is a contradiction. You are assuming that a and b n naught does not have a prime factorization, because it belongs to S. Now, if they do not have, notice that a and b they are less than n naught. Now, they do not have prime factorization. So, they have every right to be the element member of S, but n naught is the least. Therefore, that again a contradiction. So, if they do not have prime factorization, then A belongs to S, which is a contradiction, as n naught is the least. So, now every integer will have prime factorization, that is what this is the proof which we are all aware of. And now, the uniqueness, I mean, that is also kind of easy. Suppose there are two P1 to PR and Q1 to QS. There are two prime factorization, then definitely P1 is going to divide some of the Qi, but Qi is a prime. So, it cannot be divisible by any other number. So, P1 has to be Qi. Similarly, you take out now P1, if you take out and I you have taken out from the right hand side, you have P2 to PR is equal to Q product of Q1 to Qs without I without Qi. Then the same argument P2 you take, it is going to divide some prime, and the other side is a prime, therefore, it has to be same. So, what you will get that this is the unique. So, this is unique factorization. Anyway, so this we know it well. So, now of course, at a very early stage in our school, we learn that the number of primes they are infinite. That is the Euclid's argument that prime are infinite. That is simple. If not, let P1 to Pn be primes, be only primes, and Pn is the largest. Okay. So, therefore, consider this number, this is what Euclid said, P1 into P2 into Pn plus 1. Now, this is a natural number, P is in n, and then this P is going to have prime factorization. So, now if and we have only primes at our hand is only P1 to Pn. So, now you can see that P is not divisible by P1, P1 does not divide P or Pi does not divide for I is equal to 1 to n. Therefore, all the existing prime what we are assuming to have at our disposal, none of them is going to divide P. Therefore, P has to be a prime. So, P is a prime. P is a prime, but P is bigger than Pn, which is again a contradiction. So, that we are familiar from our school days, there are infinitely many primes. Now, it is except for P 2, all the primes are odd. So, there are infinite number of odd primes. So, now the odd prime, they can be divided into two disjoint sets. That means, either if P is a prime, then P either belongs to 4n plus 1, that means P is of the form 4k plus 1 for some k, or P belongs to 4n plus 3. So, I will denote 4n plus a is equal to 4k plus a, such that k varies over n. That is what the notation we are following. So, one of them, because they are which is odd, P is an odd prime, let us write odd prime, then either this belongs to this. So, natural to ask is both 4k plus 1 rather 4n plus 1 and 4n plus 3 contains infinitely many primes, or one of them contain finitely many prime. Because simple logic says that if there are infinitely many primes, then obviously one of them has to contain infinitely many primes. So, now it can happen that one of them contain only finitely many prime, or the one is contains infinitely, or both contains infinitely many prime. So, first let us look at 4n plus 3 and let us play the game Euclid had given us. So, suppose 4n plus 3 contains finitely many primes, say P1 to Pn, and Pn is the largest. Now, you consider 4 product of I from 1 to n P I plus 3. Now, obviously, P belongs to n. So, this is going to have prime factorization. Now, whatever the prime factorization is, that P is equal to q 1 to some q s prime factorization. Now, obviously, as we can see that if q any q I, they cannot be of the form does not belongs to 4 n plus 3, because it will be one of these P1 to Pn, and this is going to divide the first part, and if I take actually just throw out 3 from my list, still I am not going to lose anything. So, you can take that none of them 3. So, therefore, these QIs they cannot be of the form 4 n plus 3. Therefore, all these QIs they are going to be of the form, because the only class which remains is the 4 n plus 1. So, all the QIs they belongs to 4 n plus 1. Now, you take 2 element from 4 n plus 1. So, let us say Q1 Qi is equal to 4 Ki plus 1 for I equal to 1 and 2 for some Ki belongs to n. Then Q1 Q2 this is going to be 16 K1 K2 plus 4 K1 plus 4 K2 plus plus 1. So, this is going to be again of the form 4 L plus 1. So, therefore, what is going to happen is that Q1 Q2 this is going to be 4 K plus 1. So, you keep on multiplying it, you will land up in 4 K plus 1, but here your P is of belongs to 4 K plus 4 n plus 3. Therefore, there is, so this cannot have a, this will imply that P cannot have prime factorization. Which is a contradiction to the fundamental theorem of arithmetic. So, therefore, this is contradiction to the fact that we have assumed that 4 n plus 3 contains finitely many. So, this implies 4 n plus 3 contains infinitely many primes. So, let us ask ourselves, okay, so this contains, this class contains infinitely many prime, what about 4 n plus 1? So, in the next lecture we will address this question, which will not be as trivial as 4 n plus 3. Thank you.